You guys have repeatedly requested this particular video topic since essentially the beginning of my channel, so finally, today I have it for you guys. We are going to be talking about ancient marine animals called eurypterids. In other words, giant sea scorpions, which I know sounds terrifying, but also incredibly interesting. So let's get into it. Eurypterids are an extinct group of arthropods, and they were dominant in marine environments from around 465 million years ago in the Ordovician period of the Paleozoic Era until the end of the Permian period around 250 million years ago. And they're often called sea scorpions due to their scorpion-like appearance. However, they are not directly related to true modern scorpions. They are arthropods, as are true modern scorpions, but they aren't directly, they didn't evolve into true scorpions. They're just arthropods. They're in the same big bucket or phylum as true scorpions. And they had exoskeletons made of chitin, just like modern arthropods. Picture like a big scorpion-like lobster, essentially. And these exoskeletons provided them structural support and protection, which we'll get into later how these things helped them become really successful. They also had jointed appendages for versatile movement, so not only were their bodies jointed, kind of like trilobites, but they also had paddle-like structures for swimming, as we can see in this one example of the fossil here. And this helped them with swimming and different movements and helped them to be a little bit better at moving around and faster, and so that helped them hunt as they preyed on other smaller organisms like trilobites. They also had, and this part's pretty key to their hunting strategy and feeding strategies, they had chelicerae, which are kind of like modern arachnids have chelicerae, which are like these, jaw pincher looking things near their mouths for catching and kind of maneuvering prey. And eurypterids also had these, and many of the species of eurypterids had these like pincher things, kind of like crabs, on the end of their chelicerae, which really helped them in catching and grasping and maneuvering prey. So those are really advantageous as well. But one of their most impressive features was their size. And not just how big they got, but also how small. Their size range was incredible. Species range from just a few centimeters in size to over 2.5 meters or 8 feet long. And this size diversity, especially the larger sizes, not only gave them an advantage as predators over smaller prey-like animals, or the smaller sizes giving them an advantage in getting away or hiding from predators, but their just pure diversity of sizes allowed them great ecological versatility. That is, they could play different ecological roles depending on their size as predator, as prey, as well as in terms of their diet and their dietary versatility, their different feeding strategies, which they also got from their morphological diversity. As you can see here, they all had very different appendage types and different types of chelicerae, some with spines, some without spines, some with pinchers, some without, and this allowed, again, more feeding versatility and more ecological versatility and diversity, which allowed them to kind of dominate during their most diverse periods. And their size clearly correlated with time. We can see that early on in the Ordovician period and Silurian periods, around 450 to about 420 million years ago, they remained pretty small. And then they peaked in diversity in the Silurian and Devonian periods from about 440 to 360 million years ago, but most of them still, even though they were really diverse, remained small. It wasn't until kind of the mid to late Devonian and into the Carboniferous that the very large species of eurypterids evolved and lived during that time. And we'll talk about why they trended toward larger sizes evolutionarily later. But this figure down here to the bottom right gives a little bit of a hint. But first, let's talk about what made them successful. What evolutionary adaptations did they have that made them so successful during especially their most diverse period in the Silurian and into the Devonian? One thing was their streamlined bodies and paddle-like appendages for mobility, for movement, as well as mentioned earlier, their chelicerae for grasping prey, which obviously, again, varied in form in different species. Not only their chelicerae, but also their other appendages that they had in addition to their grasping chelicerae. They all varied depending on the species quite a bit in morphology, in kind of form, with some with more spines, some with less, some with none, and this really helped them have such a variety of feeding strategies that they did really well because they were so diverse. As we've talked about in many of my videos where I talk about one particular group of organism, whenever it comes to success and why they were successful, diversity is always on the list. Just the fact that they had so much morphological diversity really helped them sustain their dominant position for longer, because when you have a lot of diversity, you can handle certain ecological or environmental changes more easily, because maybe some types or species couldn't handle it that well because they were specialized for blank conditions, but others could because they were specialized for other conditions or other feeding strategies. And so just diversity is really one of the reasons they were super successful. Habitat versatility is another thing. So just like with the versatility they had with their feeding strategies because of their diverse appendages, they also had habitat versatility, meaning that some lived in benthic environments on the seafloor, whereas some swam and lived in kind of more open ocean pelagic lifestyles. They also had defense mechanisms like spines for protection against predators. And one thing that I find incredibly cool that I didn't even know that we could learn from the fossil record is apparently they also, or some of them potentially also, possessed the ability to camouflage. And we know this based on microstructures preserved in their exoskeletons and patterns that suggest they had some sort of coloration pattern that might have allowed them to camouflage, which is really cool. This is not uncommon per se among marine organisms. A lot of hypotheses suggest that most organisms like today have like a darker top side, a lighter bottom side, a very simple camouflage method, not necessarily something really advanced like octopuses, but just a very simple pattern that probably, based on their diversity, varied depending on the species, but it's really cool to think about the fact that they could have camouflaged. But again, this is kind of a little bit more conjecture, but this is probably or potentially another reason that they were super successful. And they also possibly had social structures that helped them become really successful based on evidence of grouping in some species in the fossil record. And lastly, they had variability in reproductive strategies. Some gave birth to live young, while others gave birth to eggs that hatched externally. This, again, just gave them a better chance of surviving various conditions. Again, diversity is key. But were they predator or prey? Well, Eurypterids likely played the role as both predator and prey, kind of simultaneously, but also depending on the period. Early on in the Ordovician and Silurian periods, from about 465-ish to 420-ish million years ago, Eurypterids were likely the apex predators, the top predators, beating out the remaining anomalocarids. If you remember from my first apex predator video, which I'll link up to the top right if you want to check it out, we talked about the very first large animal apex predator type organism, which was the anomalocarid group. Again, a type of arthropod, very similar in a lot of ways to the Eurypterids, or at least the ecological role they played. But the anomalocarids only lived for about 15-ish million years, a very short time range, yet they were very dominant during the time that they lived. They evolved in the Cambrian and then went extinct very shortly after the Cambrian in the Ordovician period, and they overlapped slightly with the Eurypterids, but at that that point, they had been declining for a bit, and the Eurypterids kind of took over the top predator spot. One thing that helped Eurypterids kind of beat out the anomalocarids was one, that the anomalocarids were likely declining already at that point, but also Eurypterids had these, grasping appendages that probably gave them a little bit of an advantage over the anomalocarids, even though the anomalocarids did have appendages that could potentially grab things, but the Eurypterids just had a design that was potentially slightly more functionally efficient at grasping and manipulating prey. And despite being relatively small early on, again, we're talking about the Ordovician and Silurian, so the timing when they were pretty small, they were still larger than most organisms at the time. Remember that this sea early in the Paleozoic, from the Cambrian to Silurian, looked very different than modern oceans, modern marine ecosystems, where we have much larger organisms like sharks. Sharks and very, very early fish were evolving as early as 450 million years ago, but they were much smaller at that time and didn't get very big and predator-like until the Devonian and pretty much every period after that. But up until then, up until the end of the Silurian, they remained pretty small. And so the lack of vertebrate predators, specifically like large fish at the time, allowed Eurypterids to take the top predator spot after anomalocarids went extinct. But as fish evolved in the Devonian, things took a drastic turn. Eurypterids faced immense competition, especially from the jawed fish. Initially, fish were jawless, and then jaws evolved. I talk a lot more about this in my evolution of sharks video, which you can check out. I'll link it to the top right if you're interested. But what's interesting, and as we saw with the size trend in terms of the evolution of Eurypterids, we saw that they got larger, especially in the Devonian and onward. Only the larger species were surviving at that point, and probably the primary reason was from evolutionary pressure from these larger predator organisms like jawed fish. For example, the placoderms, which are these large armored jaw fish that likely led to the larger sizes of Eurypterids as they evolved. However, even though the Eurypterids were getting much larger and, trying to keep up with the placoderms and other jawed fish, they couldn't really compete or out-compete the jawed fish. And this was due to a lot of reasons. One, the presence of jaws and teeth allowed for more versatile feeding mechanisms. They could bite, they could crush, and they could tear prey, allowing for a broader dietary range. They also likely had more efficient locomotion, more streamlined swimming, allowing them to swim and hunt better. Again, fish just have a very efficient body for swimming. The fins, the tail, everything is very streamlined, and anomalocarids and Eurypterids early on were streamlined compared to previous organisms and smaller prey-like organisms, and could hunt at that time in the oceans. But going up against fish, you just can't beat that. You can't beat the efficiency, the swimming and mobility efficiency of a fish's body. And that's what was evolving. So obviously that was hard to keep up with. They also potentially had better eyesight and other senses, so sensory adaptations that allowed them to beat out the Eurypterids, and they were diversifying. Fish were diversifying greatly in the Devonian during this time when Eurypterids were declining. And then at the end of the Devonian period, around 360 million years ago, a huge mass extinction occurred, the late Devonian mass extinction, which just exacerbated this separation between the groups. It just allowed fish to dominate even more because it completely diminished the numbers of Eurypterids even more. So it just separated them even more in terms of who was the better predator, And due to their steady decline throughout the Devonian, they nearly went extinct at this extinction event at the end of the Devonian. We can see over here in the figure with the timeline at the top that at the end of the Devonian, around 360 million years ago, a lot of those lines, a lot of those lineages just stop, and only a few of kind of the larger groups continued to straggle on until the end of the Permian, which was the end of the Paleozoic Era around 250 million years ago. The reason they all went extinct at that point was because of another mass extinction event, the end Permian or Permo-Triassic mass extinction event around 250 million years ago, which was the largest mass extinction event of the Phanerozoic Era, or of the last 550 million years. And this took out nearly 95% of all species on Earth, including Eurypterids. This 95% number, disclaimer, is a little misleading when it comes to a single event. It was kind of a couple different extinction events that occurred right after one another, and I talk about this protracted extinction in my Great Dying or End Permian Mass Extinction video. If you want to check it out, I'll link to the top right for you. But even though the Eurypterids went extinct at the end of the Permian, the impact they had on ecosystems and life as a whole continued on. As both predators and prey while they were living, they drove adaptations in other marine life like trilobites and other prey organisms. Predation is one of the major evolutionary drivers in terms of the evolution of, for example, spines in trilobites or other defense mechanisms. And they also drove the evolution of predator organisms like fish. The fact that they continued to diversify and continued to evolve different defense mechanisms made fish and other predators evolve new ways of preying on them and hunting them. So obviously they had a lasting impact. And as they declined and went extinct, this opened new niches for other organisms. In the Devonian, during their decline, fish were taking advantage of this, and then later, after their extinction at the end Permian, marine reptiles took advantage and took over as major marine predators in the Mesozoic, as well as sharks and other big fish. But although super successful Paleozoic arthropods like trilobites and Eurypterids went extinct at the end of the Permian, today arthropods remain the most diverse and abundant phylum on Earth. So if you want to learn more about modern arthropods and all the different groups of arthropods that we have out there today, you can check out my arthropod video, which I will link up here to the screen somewhere. And with that, guys, thank you so much for watching, and I'll see you guys in the next one. Bye.